My topic is cancer registration and age adjustment. When we think about comparing cancer rates in different states or counties or cities or even smaller geographic areas, we often want to know, does my area have more cancer than the state as a whole or the country as a whole? And in order to make comparisons like that, we have to first have the cancer data, and that's where cancer registration comes in, and we have to adjust the cancer case counts based on the age of the population, and that's where age adjustment comes in. So I'll explain both of these concepts. Cancer incidence specifically refers to how many people have developed cancer. In other words, the total number of new cases, whether the people with cancer ultimately died of it or whether they survived. So our objectives today are to define cancer incidence and describe how it is measured, and define cancer mortality and describe how mortality is measured. Cancer incidence is the number of new cases over in a given time period, and cancer incidence rates can change over time based on the evolution of diagnostic techniques. So when new diagnostic technologies are introduced for cancers that might previously have been undetected, the cancer incidence rates in an area will seem to increase. Mammography detects many breast cancers that never would have been noted. Prostate specific antigen tests, blood tests for prostate cancer, detect prostate cancer cases that never would have come to light otherwise. And so as new screening technologies have been introduced, the rates of various cancers have appeared to increase, and this increase is largely artificial due to changes in the technology. It's just diagnosing disease earlier than it would have been diagnosed before. Some cancers are diagnosed because of symptoms rather than being detected early by screening. Some diagnoses are presumptive or clinical, meaning that we don't actually know for sure by obtaining a tissue specimen, perhaps because the patient wouldn't consent to a biopsy. And sometimes, finally, there are cases that are detected only at autopsy. The person dies of unknown causes, and autopsy reveals that the cause of death was cancer. Autopsy also sometimes detects previously unsuspected cancers in people who died for other reasons. So a person could die from an accident or from another disease like a heart attack, and then at autopsy they might be found to have cancer. So who keeps track of cancer incidence? Well, in most states, cancer is a reportable disease by law, and cancer cases are reported to the Central Cancer Registry in every state, or in almost every state. Some states with very good cancer registries that have been selected by the National Cancer Institute will be federally funded by the National Cancer Institute through what is called the SEER program, which stands for Surveillance, Epidemiology, and End Results. So some states, and Kentucky is one of these, some states have a SEER-funded cancer registry, funded by NCI. Most other states have cancer registries that are funded by the CDC, and it's the main difference between the two is that the CDC-funded cancer registries do not necessarily keep track of what happens to the cancer patients after they're diagnosed. So the NCI-funded cancer registries will follow people through treatment and find out if they survive or when they die. And generally the CDC doesn't fund studies of treatment and survival. They just fund registration of the new cases to keep track of incidence. Now, once the states collect and process the cancer data, they report it on to the North American Association of Central Cancer Registries, NAACCR, or NACER for short, and the Canadian provinces also report their cancer data to NACER. So, as I said, the National Cancer Institute funds cancer registries in certain states like Kentucky, and also in several metropolitan areas like Atlanta and Detroit, for example. that have outstanding cancer registries, and these are affiliated with the Surveillance, Epidemiology, and End Results Program, or the SEER program of NCI. The Centers for Disease Control and Prevention, or CDC, funds the cancer registries in most other states through its National Program of Cancer Registries. And then the North American Association of Central Cancer Registries, or NACER, receives and publishes the data from most of the state registries and also from Canadian provincial registries. So they generate a report every year called Cancer in North America. So the SEER program has, or started with 9 states: California, Connecticut, Hawaii, Iowa, Kentucky, Louisiana, New Jersey, New Mexico, and Utah. And there are 3 metropolitan areas. I mentioned Atlanta and Detroit, and then also Seattle metropolitan area, all funded by the SEER program by NCI. And then in 2 states, Alaska and Arizona, there are cancer registries that keep track of Native American cases only, and they're also part of the SEER program. So there's a map showing the SEER registries and explaining when they were first included. So the SEER program started in the 1970s with the states and metro areas shown in red. Connecticut is the oldest cancer registry, not only in the country but in the world. The statewide Connecticut Cancer Registry dates back to the 1930s. Cancer registries in other regions, like Detroit, Atlanta, Los Angeles, and the San Francisco Bay Area, Seattle and Western Washington, and in states like Iowa, New Mexico, and Utah and Hawaii, were all funded by SEER from the very beginning back in the 1970s. Other states were added around the turn of the 21st century. So Louisiana and Kentucky and New Jersey were added around the year 2000, and cancer registration became statewide around the year 2000. And so these regions are shown in yellow. And finally, the states shown in blue, Alaska and Arizona, are those where only the Native American cancer cases are reported to the federal government. And just for completeness, we'll mention about cancer mortality, which is self-explanatory. So cancer mortality is based on how many people have died of cancer. And it's not just the deaths due to cancer, but the deaths that are associated with cancer. And mortality is easy to measure and easy to define. Incidence is a little bit harder to ascertain. As far as who tracks cancer mortality, it's the same agencies that track all of the deaths in the country. All deaths are first registered by counties, and then the counties report to the states, and the states send their data on to the National Center for Health Statistics, or NCHS, which is one of the Centers for Disease Control and Prevention, or CDC. The National Center for Health Statistics then serves as a clearinghouse to report data on mortality among people who've crossed state lines. So if a Kentucky resident dies in a traffic accident in Indiana, Indiana will report the death to NCHS, but it will eventually, the information will eventually be sent back to the state of Kentucky by the National Center for Health Statistics, and the opposite is also true. And the same applies to cancer incidence, the cases of cancer when people cross state lines for clinical treatment. Incident cancer cases are reported by hospitals and laboratories. Sometimes a specimen biopsy might be done in one state, and the specimen might be sent to a central laboratory in a different state. And the laboratories report to their state cancer registry, and then the states report they have reciprocity agreements to report the data to each other. So eventually it all gets sorted out. Now, so far we just talked about the counting of cases, the registration and the counting of cases. But if we want to know which region, which state or which county, or a smaller area like a city or a small town, or if we want to know who has more cancer, or if we want to know which race has more cancer, or whether males have more cancer than females, or if we want to know how cancer changes with age, what we need for this purpose is age-adjusted rates. So we start with what are called age-specific rates. This is a graph from the website of the Indiana State Department of Health. They have a cancer registry funded by the CDC, and in their annual reports they have some very nice graphs, and this is one that was published a few years ago. It's the data from 1998 through 2002, so it's a little bit dated, but the curves are beautiful. And so the curve shown in yellow is everyone of whatever race or gender, and it shows the age-specific rates, which start, these are rates per 100,000 person years. So the rates begin at a very low level, and it's not quite zero, but it might as well be. Very few children get cancer. And so cancer is very rare in childhood, and the rates stay down in very low levels until the late 20s and early 30s, when the rates begin to creep up. And eventually, you can see by the time people are in their late 70s and early 80s, the rates are measured in thousands of cases per 100,000 person years, which means that in this example, about 2.5% of people are developing cancer every year by the time they get to their 70s and 80s. The additional curves that are shown in other colors reflect different race and sex strata within the Indiana population. So the two upper curves, the red and black curves, are for males, and the one that's shown with a black dashed line connecting black triangles is the African American males. So they have the highest age-specific rates, and then the running a close second are the white males, these red diamonds connected by red dotted lines, and so the white males also have rates that start very low levels in the early years of life, and then begin to go up in middle age, and by the time people are in their 70s and 80s, the rates are quite high, but not quite as high in the white males as they are for the black males. So we get the impression that black males have more cancer than white males. And then never mind the race, but gender is a much bigger effect. So the females have much less cancer than the males, regardless of the race. And the African American females are shown in the dark blue, and the pale blue is the white females. And we can see that the rates for black and white females run close together in almost every age group until we get over age 75, and then the black females, the really elderly black females, have the highest rates. Now, it's interesting to look at these graphs. We could look at them in a table also and see at every age how the races and how the sexes compare. But it would be nice to be able to sum up all these age-specific rates with just one number for each segment of the population, for each race, sex, stratum, to have just one number. And what we need to do then is to average the age-specific rates over the entire lifespan. So we could do a simple arithmetic mean to average the ages, but there aren't equal numbers of people in all the age groups. And it depends on what sort of population you have in your region. There are some regions where people tend to be more elderly people in the population. There are other areas where there tend to be more young people in the population. So if we want to compare two more populations in different areas, or even if we want to compare two races or two sexes in the same area, we need to allow for the fact that there are different numbers of people in each age bracket. So we need to do what's called age adjustment, which in very simple terms is to make a weighted average of the age-specific rates. So there are two methods of age adjustment. There's direct age adjustment, and as you might surmise, there's also an indirect method for age adjustment. They're used in different scenarios. Direct age adjustment is when we want to compare two or more populations, generally two or more rather large populations, and we adjust the age-specific rates using weights. We make a weighted average using weights that are derived from an external standard population. And with this, we're able to make synthetic estimates for the purposes of comparison. So what I mean by a standard population is a set of weights based on the distribution of the age groups in the population of a specific region. So you can see first the U.S. standard population this is based on the year 2000, but it's the percentage of the population that falls into each age bracket or fell into each age bracket in the United States in the year 2000. So you can see that slightly less than 7% of all U.S. residents were under the age of 5 in the year 2000, and about 1.5% were over the age of 85 and up. And we have all points in between. The most heavily populated age groups, as you might imagine, were the baby boomers. So in the year 2000, the baby boomers were in their late 30s and early 40s. And so there's 8% of the population that was aged 35 through 39, and 8% of the population was aged 40 through 44 that year. And every other 5-year age group has less than 8. And by the time we get over age 50, we're dropping down below. By the time you're in the late 40s, it's 7% again, and by the time we get down to our 50s, it's 6%, and by the 60s, it's 3%, and by the time we're over 80, only about 1 or 2% of the population is over age 80 in each of these 5-year age groups. So we use these rates. We use we use the age distribution of the population in a particular country as our standard population for age adjustment. And it isn't always the U.S. population that we would use. We would use the U.S. population to compare one state to another. And you'd use the Canadian population if you were comparing rates in 2 different Canadian provinces. If you're comparing a couple of different European countries like France and Germany, you might prefer to use the European Union standard population. Now, the U.S. and Canadian standards are based on a census. Apparently there isn't any such thing as the European census, no single census for all the European countries. So great minds have decided that the European population is going to have 8% under age 5 and 7% in each age bracket up through age 54, and then the percentages began to drop rather abruptly, so 6% in the late 50s, 5% in the early 60s, 4% in the late 60s, 3% in the early 70s, 2% in the late 70s, 1% each in the early and late 80s, and so that's the best estimate that they use for the European Union. And these are the weights that we would use to compare 2 European countries to each other. Finally, if we wanted to compare countries on different continents, like if we wanted to compare Germany and Gambia and Guatemala, we would need to use a worldwide standard. Now, if there wasn't a European census, there certainly isn't a worldwide census. But again, great minds come to the rescue and estimate what they calculate the percentage of the world population would be in each age bracket. And so the World Health Organization has published a standard population that estimates that almost 9% of the people in the whole world are under age 5 versus less than 1% in their early 80s and more like 0.5% in their late 80s. And again, we have all points in between. And the baby boomers were a U.S. phenomenon, so we don't see the baby boom generation in the Middle Ages in the world standard population. So if we were comparing countries on different continents, we'd use the world standard. If we're comparing 2 European countries, use the European Union standard. Comparing 2 Canadian provinces, use the Canadian standard. And if we were comparing 2 states in the United States, we'd use the U.S. 2000 standard. So I'm going to show how we do age adjustment in the state of Indiana. And I'm starting with, I'm doing a comparison of white males and black males. I want to see who has more cancer. And I start with just the numbers of cancer cases in each age group. So the age groups are numbered down the center column of this table, and the table will build from the middle working out. So the whites are going to build up the columns of the table marching leftward, and the blacks are going to build the columns of the table marching out to the right. And we start with the number of cases in each age bracket. And we see that at the bottom we sum them up, so we can see that in every age bracket there are more cases among whites, more total cases among whites than blacks, at least in the males. And at the bottom we see that there are almost 65,000 cases among white males, but only 5,000 cases among black males. So it's about 13 times as many cases among white males than black males. in Indiana during this 5-year period, 1998 to 2002. Count them, that's 5 years. So that's just the number of cases, but those aren't rates. We haven't factored in the population yet. So let's look at the population. So I'll change to the next slide. And we have the population in every age group. And you can see there's more whites than blacks in every age group in the state of Indiana. And the grand total of all the white males is more than 2.5 million, and there's only like 250,000 black males. So there's about 10 times as many white males as black males in Indiana, and there were about 65,000 times as many, or 13 times as many cases among white males than black males. So if you do the math and just calculate you think in terms of a crude rate, it's probably going to be higher among the white males than the black males. We'll get there in a moment, but first I have to do one more thing. Remember, it is 5 years worth of cancer cases, but the population, this is the year 2000 census population. So the census was done in 2000, and we have 5 years worth of cancer cases. So we have to multiply that population by 5 to get the number of person years on average. We'll just use the year 2000 population as the midpoint. We'll multiply that midpoint population by 5 to estimate the number of person years. So watch right here in this frame. When I click to the next slide, you'll see instead of 200,000, we'll have about 1 million. So I predicted that accurately. We have about 1 million in that cell. Which cell was it? So there's about 200,000 in each of those cells. Now it's about 1 million in each cell. We multiplied it by 5. So there's about 1.3 million, or rather 13 million person years among the white males, and only 1.3 million person years among the black males. 10 times as many people, but 13 times as many cancers. So the white males must have more total cancers per 100,000. But we can do the rate per 100,000. We can divide the number of cases by the number of person years, and we're going to get a rate per 100,000, and we can compare those age-specific rates per 100,000. And a funny thing happens now, because the total number, the 65,000 divided by 1.3 million, gives us a rate of about almost 500 per 100,000 for the white males, and the 5,000 cases in the 1.3 million black males gives us about a rate down to almost 400 per 100,000 for the black males. It still looks like with these crude rates shown in pink, it still looks like we have, this is not a weighted average, it's just a crude average, or an arithmetic mean of those numbers, unweighted. It looks like the whites have a higher rate than the blacks. They do have a higher crude rate, but it hasn't been age adjusted yet. Now the reason why that matters is, let's look at the individual years of age. Let's start at the top and work our way down. Let's start with the 85-year-olds. So the rate for white males in the 85 and up age group was 3,000 per 100,000, a little more than that. But it's actually 3,400 per 100,000 in the black males. So black males have more in that age group. They have more cancer in that age group, higher cancer rates in that age group. And for the 80 to 84 age group, both races have about 3,200, but the whites are slightly less, the blacks are slightly more. So the blacks are still higher in the 80 to 84 age group. In the 75 to 79 age group, it's 3,051 per 100,000 for the white males, 3,566 per 100,000 for the black males. Black males have much more cancer in the late 70s, and likewise in the early 70s, likewise in the late 60s and the early 60s and the late 50s and the early 50s, the late 40s, the early 40s. And it's only among the very young, well, not very young, but among the younger white males, the rates are about equal to the black males. And then in those in their 20s and younger, the rates are actually higher among the white males. So young white people have higher age-specific cancer rates than older white people. But older black people have higher age-specific cancer rates than older white people. And most cancer occurs among the elderly segment of the population. So it makes sense to do a weighted average that takes account of these differences. And so we're going to need to use the weights. And because we're making a comparison within a United States state, namely Indiana, we'll use the U.S.A. 2000 standard population. So we'll use as our weights the percentage of the population, percentage of the total U.S. population in the year 2000 that was in each age group. And we're going to multiply these age-specific rates by the corresponding percentage in the standard population to get these product terms that go out in these columns out on the far right and the far left, and we're going to add up those product terms to get a sum at the bottom. And this is our weighted average. This is our age-adjusted rate. So the age-adjusted rate among the white males is 536, and their age-adjusted rate among the black males is 635. And now for the first time we see clearly that the black males actually have more cancer than the white males. They have a higher age-adjusted rate. And that fits with what we saw looking at the curves on that graph. So the age-adjusted rate is a weighted average. I can do the same thing for the females. So again, we have the age group listed down the middle, the number of cases, and again we see it's about 65,000 cases among white females and a little less than 5,000 among the black females. And we compare the populations, and the population is about 10 times as high among the white females as the black females. And it's true when you say person years also. And then when we do crude rates, again, the white females have a higher crude rate than the black females. It's over 400 per 100,000 for the white females and just a little over 300 per 100,000 for the black females before age adjustment. But when we bring in our age specific, when we bring in our standard populations and multiply the percentage of each age group that's in the standard population times the rate in each age group, then we accumulate these product terms and get our age-adjusted rates, and they wind up being about the same. 418 per 100,000 in the white females, 413 per 100,000 among the black females. It's about the same. It really just doesn't matter. But there really isn't a racial disparity among the females, but you wouldn't know that until you do the age adjustment. So the racial disparity that appeared to be among the white males turned out to be, after age adjustment, turned out to be among the black males, and the apparent racial disparity among the white females disappeared after age adjustment. It turns out the white females and the black females have about the same rate. So that's the direct method for age adjustment, which is useful for comparing large populations. If we wanted to compare two countries, if we wanted to compare two states within the United States or two provinces within Canada, the direct age adjustment method is the way to go. And even comparing two racial groups that have millions of people in each of those states, we can do blacks and whites, or males and females, or all of the above. We can do that with direct age adjustment. So why would we ever use indirect age adjustment? The answer has to do with small numbers. When we have small numbers of people in our local population, if we have a rural county with only a few thousand people, or if we have a small town with only a few thousand people, or maybe we have a workplace where there's not very many people, and someone suspects that there's a cancer cluster in a small area. This happens a lot. This is a very common problem in public health, that people in a small town or people in a specific workplace think there's a cancer cluster. They've noticed that there are a dozen cases of some type of cancer in the population that's known to them in a short period of time, and they become concerned because they think that's more than the expected number of cases. That's where indirect age adjustment becomes useful. So when we have one population where we suspect that there may be an excessive amount of cancer, perhaps a cancer cluster, what we want to do is make a comparison to external referent data, meaning we'd like to compare our small rural county or our small town or our workplace with a few thousand people or a few hundred people. We'd like to compare the occurrence of cancer in our small population to a much larger outside population, like the state as a whole, or maybe even compare it to the whole country, and say, how much cancer would we expect? How many cancer cases would we expect to see in our community or in our workplace if the national or statewide cancer incidence rates were holding true for our population, considering the age, sex, and race structure of our local population. So what we want to do is contrast our observed number of cases, the number we could count in our small local population, versus the number that would have been expected had the statewide or nationwide rates been operating on the people in our small local population. So with indirect age adjustment, we have to calculate the expected number for comparison with the observed number, and we're going to do a ratio of the two. Now when we do indirect age adjustment, I just show an example, and the table is just already made up for, I do one race sex stratum at a time. So I have now for the white males, I'm going to show also for white females, black males, and black females in these different panels, but I'll start with the white males. So this is just a made-up example using data from a fictitious county somewhere in Indiana. I called it Petunia County, and I said, suppose Petunia County has just a few thousand people, so it has about 900 white males, and it has a certain number of white females and smaller numbers of black and white males and females, or smaller numbers of black males and females. And we're going to take the statewide rate from Indiana as a whole that's applying to each of these age groups. So we have the countywide population in each age group in these cells in this column. We multiply by the statewide rate, which is per 100,000, remember. So we multiply by that statewide rate and divide by 100,000 to get the expected number of cases in each age group. And so when we add up the expected number of cases among white males in each age group, we get a grand total. We estimate that we would have expected to see 6.7 cases among white males in our rural Indiana county that I made up. These are all made up numbers, but we would have expected to see 6.7 cases among the white males, and using the same reasoning, we would have expected to see 1.3 cases among the black males, and 5.4 cases among the white females, and 1.2 cases among the black females. And we add up the expected numbers, this one plus this one plus this one plus this one, and you can do the math. 6.7 plus 1.3 is 8.0, and then we add 5.5 and 1 and some change, and so we're getting about 13.5, and now about 14 3/4. Maybe that's my best guess of what the number is going to be there. Let's add it up. So we added up officially, and it's 14.71. So I was pretty close with my estimate, probably because I've done this once or twice before. Now that's the number we would have expected. So in our small rural Indiana county that I made up, Petunia County I think I called it, we were expecting to see 14.7 cancer cases if the statewide rates for all of Indiana had applied to the age groups and the race-sex strata that existed in our small rural county. Now suppose that we had actually observed 22 cancer cases in that period of time. Then the observed number of 22 is divided by the expected number of 14.7. And I picked these numbers to make those numbers because it makes my ratio come out to a nice round 1.5. So you may be wondering what a SEER is. It's a standardized incidence ratio. I calculated a standardized incidence ratio by dividing the observed 22 cases by the expected number of 14.7 cases, and it works out to just about exactly 1.5 for the standardized incidence ratio. And sometimes you'll see a standardized incidence ratio expressed as a percentage, so it's 150%. So 1.1 would have been 110%. If we'd had 2.0, it would have been 200%. Either way is correct. 150% is the same thing as 1.5. So our standard incidence ratio in our fictitious small rural county is 1.5, and with statistical significance testing we could ascertain whether that's truly a rare event, whether this is really an unexpectedly high number of cancer cases beyond what we'd expect from chance alone. So the indirect method of age adjustment is useful with small numbers of cases or small numbers in the population. It's useful in places where we have little or no information about the age-specific rates in the local population. It's a method that requires us to calculate a ratio of the observed to expected cases, so we have to calculate an expected number for comparison with the observed number. And by so doing, we calculate a standardized incidence ratio, or SIR. And the way we interpret the SIR is if it comes out 1.0 or 100%, it means incidence in our local population is equal to that expected based on the reference population. Greater than 1.0 indicates unexpectedly high incidence of cancer in our local population compared to the larger referent population. A standardized incidence ratio less than 1.0 indicates lower cancer incidence in our small local population compared to what we would have expected had the rates in the larger reference population applied to our locality. So, just to sum up, the direct method allows comparison between populations if the same standard population is used, like to compare blacks versus whites, males versus females, or Kentucky versus Indiana, or compare any two states or provinces or countries. The indirect method is used for small numbers or poor data and allows comparison only between the local population and a reference population. An example is to compare your county to the whole state. You can compare your state to the whole country, or you could compare a small town to the state as a whole, and that's the example I'm going to show next. So I'm just about done with the slides. My last slide here shows some web links, shows some URLs for various websites that are pertinent to calculating cancer rates. I just call everyone's attention to the Kentucky Cancer Registry website here and the Census Data American Fact Finder website here, because those will be useful in the next little exercise that we're going to do. So our next little exercise will be to use a real community called Vine Grove, Kentucky. And I'm going to get first the population data from Vine Grove, Kentucky, so that I can calculate an expected number of cancer cases. Now, I'm not singling out Vine Grove. I just had to think of a small town in Kentucky, and I had to find one that has sufficient numbers, but still small numbers, of both black and white population. And so I don't know that many small towns, but the name of Vine Grove popped into my head, so I looked that one up. So we're going to click here. This is the American Fact Finder site for the U.S. Census Bureau, and we go to factfinder.census.gov, and here we are, and we're going to go to the advanced search. Let me pull up an advanced search. Show me all, and I'm going to put in my community. I could have, the example they had in the window was Atlanta, Georgia, but I'm going to type in Vine Grove, Kentucky, and the computer is reading my mind. It knows I was going to say Vine Grove City, Kentucky. I've done this once before, and I guess it remembered. So I'm going to, and they call it a city, but it's a small town. Let's click through to get our information. And the total population of Vine Grove is 4,520. So that's a nice small town. And what I want to do now is look at specific data. So I'm going to back up for a moment, but I'm going to start with so the advanced search is I'm beginning with Vine Grove, Kentucky, and I'm going to request data based on ethnic group. And so I'm going to choose black and white. And then, so I'm going to choose white first and generate a table for sex by age just for the whites, but it has to be based on the 2010 census. So I'm going to find the right page, and I've done this before, and I know it's around here somewhere. I'm going to scroll through the pages. They have several different years. You can get estimates for specific years, but I don't want those estimates. I want the actual census from the year 2010. So I'm going to do sex by age for the whites, but I'm going to do it in 5-year age groups. So happen to know the table that I want is number P12A. I've done this before, so I had to scroll to page 10 to find P12A. This is a table of sex by age, and it's just the whites now, and we'll come back and do this again to get the data for the blacks. But here we go, and we've got males and females. So males are shown here, and females are shown here. And you can see there's a grand total of 1,671 white males and 1,762 white females. And we have all the age groups starting with under 5 and continuing through 85 and up. And there's a few tricks of the trade where we have to, there are certain age groups that have been divided, and we'll have to add these. So when we want to know about ages 65 to 69, we'll have to add the 22 people from 65 to 66 and the 49 people from 67 to 69 among the white males. We'll have to add that and get 71. And we'll have to add the people in the early 60s, 40 and 39, that's easy, it's 79. And for the people in their 20s, it'll be the 17, 20-year-olds, the 12, 21-year-olds, and the 58, 22 to 24-year-olds. Add them all up and you get 87. And we'll add up these teenagers, these they're in their late teens. The 15 to 17-year-olds is 68, and the 16 or 18 to 19-year-olds is 39. And add those together, we get 107, if I did my math right. So it's a little more complicated, but we'll back up now. Having done that once for the whites, we'll back up, and I'll clear the selection. I'll take the whites out of there, and I'll choose this time blacks. And so it's made that selection. We close our selection box, and now I'm going to ask once again for table P12A that comes from, I'm sorry, I clicked the wrong thing, but I was trying to go to the last page here. If I click up here, it'll sit still. So I'm clicking through. I think it was on page 10. I'll find P12A. We're starting to see some. Oh, it isn't A anymore. It's B for black. So P12B is sex by age for black alone, and I'll click on that line there, and it gives me the table for the blacks. And you can see we have, as we had in our small county in Indiana that was totally made up, this is real data from the city of Vine Grove. You see, if we wanted the county data, we could just ask for it from the state cancer registry, but if we want data for a small town like this, that's a little bit different. So I'm noticing that we have several hundred, 330 something black males and 330 something black females. And again, you see we have the single year, not the single years, but the 5-year age groups, with a few exceptions where we have to do some fancy footwork and add up the 15 to 17-year-olds and the 15, 18 to 19-year-olds and so forth, add up the people in their early 20s. So there's, what, 34 in the late teens, and 7 and 3 is 10, and 10 is 20 in their early 20s, and in the 60s again. Again, there will be some tricks. There's 13 in their early, no, that's not early. There's 16 in their early 60s and 7 in their late 60s. We'll add those up. And what are we going to do with all that? Well, we're going to plug it into our Excel spreadsheet, this one. So we're going to plug in the ages, and I'll show the populations by age, and I'll show that in a moment. But our Excel spreadsheet is going to do what I did in that set of slides where I demonstrated for the small county in Indiana. Now I'll demonstrate for a small town in Kentucky using a spreadsheet. So I've made up this spreadsheet ahead of time where it does all the calculations for me. And I'm going to fill it out with the age-specific population in each race-sex group, but I'll also put in the age-specific cancer incidence rates for Kentucky as a whole, and that's our comparison group, is Kentucky as a whole. So I'm going to go to the cancer registry website now, www.kcr.uky.edu, and I'm going to ask for cancer incidence rates. Now let's pretend that in my small town of Vine Grove, I suspect there's too much lung cancer. So we had a certain number of cases of lung cancer, and I want to know if that's too many. So we had, let's say we had 25 cases of lung cancer in Vine Grove in a period of 5 years. And I'm going to choose arbitrarily 2008 through 2012 as my 5-year period, and that'll be that's a nice round number, 2 years before and 2 years after the 2010 census, because I'm using my 2010 census from my midpoint population. So I'm going to calculate my expected values based on the 2010 census multiplied by 5 for a 5-year period. And I want to get the actual numbers, or the actual age-specific cancer incidence rates for Kentucky as a whole, starting in the year 2008 and continuing through the year 2012. And I'm going to want to do that for every combination of race and sex. Now, I only did the population for black and white, males and females, and that's based on the fact that the cancer registry is only going to give us data for 2 races and, of course, 2 genders. So we're going to have, I'm going to start with white males and get the cancer incidence rates for Kentucky as a whole, age-specific rates. So this is giving me the Kentucky statewide age-adjusted rate, which is nice, and we have the age-adjusted rate in each county, and that's nice, and even puts it on a map, and that's nice too. But and we have the county data listed one by one in rank order descending down below, but that's not my statewide age-specific rate, so I have to click at the bottom and click on state data, and it'll give me, it's giving me the age-adjusted rates. Excuse me, this is all sites, and I said I was going to do lung cancer. Let me back up and do lung cancer. And that's easy to change. We scroll down through the sites, the anatomic sites, the body parts. We're interested in lung and bronchus cancer. I'm going to redraw, and so it's going to give me the statewide lung and bronchus cancer rates for white males between 2008 and 2012. And I'm going to ask for the state data, and these are the statewide age-adjusted rates and crude rates for every year, but I want the age-specific rates for lung and bronchus, so here they are. And it's going to give me the age-specific rates, and I'm going to have to combine the first age groups, the under 1 years and the 1 to 4 years, but they're easy to combine, they're zeros. So that's easy to combine, but I'm going to use this column out here and take the numbers from this column out here. And you see we start off at 0, and our highest number is 647.6, and I'm going to take those numbers and transfer them to my spreadsheet, and then I'm going to close and do the same thing. I'm going to recalculate now for white females, redraw and recalculate, and once again ask for state data, age-specific rates for lung and bronchus. I'm going to use these rates on the end here, this last column, and you see they start out at 0 and go as high as 298.5 in the white females. And then we're going to switch to black males, still 2008 to 2012, lung and bronchus. We redraw that. Now most of the counties have sparse data among the black males. We can get statewide age-specific rates, give them to us, and we start at 0 and go as high as 866.5 in the highest age group. And finally, we close that, and we'll go back and do black females and recalculate and go to the state data and the age-specific rates for lung and bronchus once again. And again, they start at 0 because kids don't get lung cancer, and they go as high as 396.4 in the highest age group. And now I'm just going to pretend I won't make you watch me type all those numbers in. I did that before, and what I did was I made multiple tabs of the spreadsheet where I've put in some of the numbers. I had one column of figures on every page. So you remember 647.6, and you remember the 298.5. So I'm putting in the age-specific rates for the white males, the white females, and there go the black males up to 866.5, and the black females up to 396.4, just like I showed in that illustration. And now we're going to add the populations as I keep moving through the tabs. So we're going to put the population for the white males, and when I fill in the populations, it has calculated for me these product terms, the expected number of cases in each age group, and then it adds them up. And so I'm expecting 9.9 cases among the white males, and I put in the population for the white females, I'm expecting 9.0 among the white females. I put in the population for the black males, where I'm expecting 1.2, and the black females, finally, where I'm expecting 0.7 cases. And the total number of expected cases is the 9.90 plus the 9.03 plus the 1.25 plus the 0.73, and we get 20.91 expected. So we were expecting, if the statewide rates had prevailed, we were expecting to get a little over 20 cases, almost 21 cases in our little community of Vine Grove in a 5-year period, and we actually had 25. And we could do a statistical significance test, but I think qualitatively we can already appreciate that 25 cases when we were expecting about 21 is really nothing to write home about. It's probably within the margin of error. And I could do the statistics, but I won't. I'm just going to stipulate that I think 25 when I expect 21 is not really excessive. If I was expecting 21 and found 63, now that would be a cluster. That would be something worth writing home about. So in a very brief way, that's the way we can apply the math of direct and indirect age adjustment. And often we will use indirect for these local clusters. But in trying to investigate or rule out a cancer cluster in a small community, the indirect age adjustment method is quite useful. So thank you very much.